linguistic compression model using finite state transducers. Nathan Daniel, Cheng, Gong, and Keyon Vafa present a CS51 final project. Why linguistics?
The topic interests us for a very simple reason. Linguistics, on the surface, feels far removed from the cold, chrome world of computers, but language, in many ways, defines mankind. Moreover, with the increasing computational powers of computers, we felt that this was a field we would hear more of in the future. The core of our project were finite state transducers which compressed and decompressed text. A finite state transducer is best described as a machine which takes a valid input and, depending upon the state of the machine, returns an output and changes its own state. The compression model, a finite state transducer, works by removing vowels and repeated consonants. So, for example, giraffe will become GRF and Alice ALC. The uncompression model, which is also a finite state transducer, contains our algorithm. It's a more complex composition of smaller finite state transducers. To create this, we needed a model of the English language, which included character probabilities, finite state transducers to handle the text, and the shortest path algorithm to find the most probable uncompressed text. So we did it by composing finite state transducers we found in the OpenFST library, which was a library of finite state transducers we were able to access using Python. This diagram briefly describes a finite state transducer. It has many states. It has input values, output values, and weights. And using that, we composed 3 different models, which I'm about to show you, that will have the overall effect. The models are as follow. In our file compress.python, we take the word and we compress it ourselves. So if I give the word Alice, it'll be return ALC. And this is done by using code and accessing the finite state transducer library. Spell.py is somewhat similar. It takes a word and it returns its character by character value. This is a little more, this might be hard to understand, but it's pretty straightforward. It takes the word, for example, text, and returns T on the first go round, and the next one would take a nothing and return E, the nothing return X, the nothing return T, and then the space. So we had a few, this is what the code generally looks like for finite state transducers. And we use it all together in our main program, which looks like this. So because this code seems a little confusing and daunting, we'll show you what our main program does. It has 3 options. We can compress and decompress a text string, or we can do half of each one, compressing string only and decompressing string only. So I'll show you guys the both, compressing and decompressing text string. That's one. So we enter the string. I'll enter a string that I know works. Alice was beginning to get very tired. Why Alice, you asked? Well, we used Alice in Wonderland as our dictionary, so if a sentence is in the book, it'll work fine. So you see here, it compresses the text with ALC, WS, this. This is just the compression model I was telling you about. And then it successfully recovers all the text, which is actually pretty impressive. And now, something that doesn't work, we'll do a word that isn't in the Alice dictionary, like Greg likes cows. So it notices that Greg's and cows isn't a valid word because of another Alice in Wonderland, but it successfully compresses the one that works. And now maybe one more, one that we haven't tried yet. Computer science is a wonderland of the future. It actually recreates, it has the 100% match recovered. So this doesn't work all the times, but a lot of the times it successfully returns the words we're looking for. My name is Keyon Vafa. I work with Nathan Daniel and Cheng Gong, and this was CS51.